All right, so for number 25, part A, we have to simplify this expression of 10 to the 3 log x plus 2 log of y. All right, so first, whenever there are exponents that are being added and they have the same base, we can just split them up and say this 10 to the 3 log of x is being multiplied by 10 2 log of y, right? And before we can start to cancel anything out, we can apply our log rules to the coefficients in front of these logs, right? And so what I mean by that is we take this 3, and because it's being multiplied by the log out here, we can take it inside the log and say that this is 10 to the log of x cubed. And we can do the same to the log y, to the 2 log y, and say that, so we have this multiplied by 10 to the log of y squared. And now we know that this 10 and this log, or both of them actually, can be canceled out, right? And so then we have a simplified expression of x cubed times y squared, or just x cubed y squared. All right, so for part B, looks like we have a lot of little natural logs and e's in there. Also, sorry, before we do that, I'm gonna kind of write this out there to make it more clear for part A. So part A is x cubed y squared, right? Just make it a little clearer. But so for part B, we can start simplifying this by kind of looking at this natural log of square root of x minus 5 natural log of x. Okay, so looks like, well, we have this 5 natural log of x, right? Natural log of x. And in the same way, this 5 can be taken in the natural log, and when it's taken in the natural log, that's going to be natural log of x to the 5th, right? All right, so now we can take a look at this natural log of square root of x minus, in this case, natural log of x to the 5th, right? And whenever we have natural logs that are being subtracted, so I'm just going to write this out. I'm going to say this natural log of, and square root of x can also be taken as x to the 1/2, right? So I have natural log of x to the 1/2 minus natural log of x to the 5th. And whenever we have natural logs that are being subtracted with each other, we know that that means we can take their insides and divide them, right? So that's going to be equal to natural log of x to the 1/2 over x to the 5th. And you can do this yourself, but that'll simplify to natural log of x, goodness gracious, x to the negative 4.5. And so then we can, I guess our expression will simplify to natural log of e2. So we simplified this whole exponent, right? So I'm just going to say natural log of e to the natural log of x to the negative 4.5, right? Okay, and then we have these e's in the natural logs that can cancel out, and so then we're just left with natural log of x to the negative 4.5, and then we can apply that log rule that we did up here, but in reverse, right? So we can bring this out in front and say that's going to be equal to negative 4.5 natural log of x, or if you want to write it in fraction form, that's going to be negative 9/2 natural log of x. Either one works, so we'll just say negative 9/2 natural log of x. All right, so for problem 26, it looks like, so we're given a log base 4 of x graph, and it looks like there's some transformations that are being applied to it, and we have to analyze those transformations. And so for part A, it says sketch a graph of x using the grid at the right. Include the asymptote. Okay, so if we look at the transformations here, it looks like it is being shifted left 2 right? And it is being reflected, but since it's on the outside, it's being reflected over the x-axis, right? So then if we draw that out, we know that this graph is going to be shifted left too. So because our asymptote starts, or our vertical asymptote for the log 4 of x is at 0, that is going to be shifted left too as well. And so we're going to have a vertical asymptote at -2 instead. And so we're going to be shifting that left, and then we're going to reflect it over the x-axis, right? And so it's going to kind of look something like, if I can draw it out, right, like this, right? Gonna kind of make the same motion, but it's obviously gonna be reflected, and then we have it being shifted left. And so it asks, what are the domain and range of f of x? So if we can see here, like I said before, this vertical asymptote is being shifted left to -2, right? And so that means the domain has to start at -2, because that's where asymptote starts, and goes to infinity. And so for a range, if we look at the possible values that it could be, it looks like, so on this left side it's going up to infinity, and then on this right side where it's like closer to 5, it's going to -infinity. And so we're going to have our range from -infinity to infinity. And so part C, it asks for the vertical asymptote for f of x, and we've talked about this before. So for a regular log base 4 with no transformations, it's the vertical asymptote is at 0, right? But since we shifted it left to, that means the vertical asymptote is going to be shifted left too. And so we have the vertical asymptote at x equals -2. All right, so for part B, it says, is the average rate of change between any 2 points on the graph of f positive or negative y? Okay, so if we look at, I don't know, 2 points, let's say like 1 and 3, and we're taking the rate of change from like 3 to 1, right? Because that's how we do it. We go from like right to left whenever we're doing rate of change. And so that would be negative, right? Because f is decreasing. So that means the average rate of change must be decreasing because, or the average rate of change must be negative because f is decreasing. So I'll just say negative because, if I can spell, I am doing math, so because f is decreasing. Okay, so for part E, it says, do the rates of change increase or decrease when moving from left to right on the graph of f? Is the graph of f concave up or concave down?
And then I can see, because I'm looking at the rates of change of my graph of f, I notice that they are increasing as I move from left to right. So the rates of change are increasing as we move from left to right, right? And I can also say, because the rates of change are increasing, my function is going to be concave up.
All right, so for problem 27, it says the 2 most intense earthquakes in the world were recorded just 4 years apart. A magnitude 9.5 on the Richter scale hit Chile in 1960, and a 9.2 magnitude earthquake hit Alaska in 1964. And it asks, how many times as intense was Chile's earthquake compared to the Alaska quake? 3 decimals. Okay. So, and it gives us 2 helpful equations right here. It gives 10 to the magnitude is equal to relative intensity, and also magnitude is equal to the log of relative intensity. And so for this, it's asking for how many times as intense was Chile's quake. So that means we're going to be using this first equation right here to be solving for intensity first. And so I'll just say relative intensity for Chile is going to be equal to 10 to the magnitude. So it says the magnitude was 9.5, so we're going to have 10 to the 9.5. So that's relative intensity for chili. And then relative intensity for Alaska is going to be equal to 10 to its intensity, which was 9.2. And so to find how many times as intense was Chile's quake compared to Alaska quake, so then what I'm going to do is just going to say, let's see, I'll just say Chile, or I'll say intensity comparison. So to find that, I'll take Chile's relative intensity, so that's going to be 10 to the 9.5. That's going to be divided by Alaska's intensity, which is 10 to the 9.2. And so if we evaluate that, we get 1.995. So then we can say Chile's quake was 1.995 times as intense as Alaska's. There we go. Alright, so now it looks like we have some log equations and we're trying to solve for x. Alright, so if we go to part A, we have this natural log of 10 to the x plus 1 is equal to 2. Alright, so if we're trying to get x by itself, the first step we're going to take here is to take e on both sides, right? Take both sides to the e. So then that's going to cancel out these e and the natural log on this side. So then we're left with 10 to the x plus 1 is equal to e squared. And then we can subtract a 1 over. So then we'll get 10x is equal to e squared minus 1. And then we can take the opposite of that 10 to the x. So then we're going to take the log of both sides. So then, and when we take the log of this 10 to the x, remember when something is in the exponent inside of a log, that means we can just bring it out and multiply. So then we'll have like x times the log of 10, which is just, log of 10 is just 1, right? So then we'll have x is equal to log of e squared minus 1. And then if we round that to 2 decimals, that's going to be 0.81. I'm going to erase this for the next problem. Alright, so for part B, we have 8 times 3 to the x is equal to 7 times 4 to the x, alright? So we're trying to get x by itself, right? So the first step that we can take is divide 8 on both sides. So then we get 3 to the x is equal to 7 over 8 times 4 to the x. And then since we're wanting to solve for x, we should probably get them on the same side. And so we can then divide by 4 to the x on both sides. So then this is going to turn into 3 to the x over 4 to the x is equal to 7 over 8. And then we can actually rewrite this, since both the 3 and the 4 are being taken to the x. We can rewrite this as 3 over 4 to the x is equal to 7 over 8. And then, since x is in the exponent, we can take the natural log of both sides, right? Take the natural log. And so then, take the natural log. So, I'm going to rewrite this. Now that we have x in the exponent, and remember the log rule of x being in the exponent, or anything being in the exponent, we can bring it in front of that natural log, right? So then we're going to have x times the natural log of 3 over 4 is equal to natural log of 7 over 8. And so then we can just divide by natural log of 3 over 4 on both sides. And then we'll get x is equal to natural log of 7 over 8 over natural log of 3 over 4. Or if we want to round that, we can say x is equal to 0.46. All right, so for part C, we have 10 to the 2x plus 5 is equal to e to the 7x plus 3. All right, so there are a couple ways you could go about this problem. So for this solution, we're just going to take the log of both sides. So then we'll have log of 10 to the 2x plus 5, right, is equal to log of e to the 7x plus 3. All right, and so since these are exponents, we can bring them out. And so that's going to be, I'm going to write this over here, 2x plus 5 times log base 10, which is just 1. So that's just going to be 2x plus 5. That's going to be equal to 7x plus 3 times log of e. All right, so now since we're trying to get x on the same side, and we're trying to solve for x, we're going to distribute this log of e to both of them. And so then we'll have 2x plus 5 is equal to 7x log e plus 3 log e. And so then we can get x's on the same side. And so I'm just going to subtract by 7x log e on both sides. And so then we have 2x log, or no, sorry, not 2x log. That's just going to be regular 2x, right? Minus 7x log e plus 5 is equal to 3 log e. And then I can subtract 5 on both sides since we're just trying to get our x's on the same side. So then we'll have 2x minus 7x log e is equal to 3 log e minus 5. All right, so on this left side, since they both have x's with them, we can just factor out an x, right? So then that's going to be x times 2 minus 7 log e is equal to 3 log e minus 5. And so then we can just divide by that 2 minus 7 log e on both sides. So that's going to be x is equal to 3 log e minus 5 over 2 minus 7 log e, or 3.55. All right, so for part D, we have 6 is equal to 2 divided by 1 minus e to the negative 0.3x. All right, so the first step we can do is take this x, or this whole term actually, out of the denominator because we don't want x in the denominator. And so then we can rewrite that and say 6 times 1 minus e to the negative 0.3x is equal to 2. And then we can divide by 6 on both sides. So then we can have 1 minus e to the negative 0.3x is equal to 2/6, or if we want to simplify that a little bit, 1/3. And then we can subtract by 1 on both sides. Subtract by 1. So then we get negative e to the negative 0.3x is equal to 1/3 minus 1, or negative 2/3. And then we can divide by negative 1. And so we'll get e to the negative 0.3x is equal to 2/3. And then we can take the natural log of both sides, right? And so then we'll have natural log of e to the negative 0.3x is equal to natural log of 2/3. And then we can, since it's in the exponent, we can bring that negative 0.3x out, and the natural log and e will cancel. And so then we'll have negative 0.3x is equal to natural log of 2/3. Or if we divide by negative 0.3, we'll get x is equal to natural log of 2 divided by 3 over negative 0.3. Or if we want to round that to decimals, that's just going to be 1.35. All right, so for problem E, or part E, we have this log of 3x plus 2 plus log of 2x minus 1 is equal to log of 2x squared plus 3. All right, so it looks like the first log rule that we can apply here is, so we have these two logs on the left side that are being added. So remember what we can do with their insides, we can multiply them. And so that's going to be log of, well, if we go ahead and factor this out, it's going to be 6x squared minus 3x plus 4x minus 2 is equal to log of 2x squared plus 3. And then we can take 10, do 10 to that, both those on both sides. So then we get 6x squared minus 3x plus 4x minus 2 is equal to 2x squared plus 3. All right, so then if we combine like terms, we can combine this negative 3x and this 4x, and then we can subtract, actually we can just take it step by step. So then, and I'm going to bring this, let's just bring it down here. So then we'll have 6x squared plus x minus 2 is equal to 2x squared plus 3. And then we can subtract 2 on both sides, 2x squared on both sides, right? So then we'll have 4x squared plus x minus 2 is equal to 3. And then we can subtract 3 on both sides. So then we'll have 4x squared plus x minus 5 is equal to 0. And so now we realize that we can factor this, right? And so if we factor this, let's see, we can get 4x plus 5 and x minus 1. And that's going to be equal to 0. And so then if we solve for x, we get 4x plus 5 is equal to 0, or if we simplify that, x is equal to negative 5/4, and then we have x minus 1 is equal to 0, or x is equal to 1. Okay, so this x is equal to negative 5/4, that's extraneous, right? Because we can't take the log of a negative, right? And we would be doing that if we had this x is equal to negative 5/4. So we can go ahead and just cross that out, and we'll just have x is equal to 1. All right, so for problem 29, says an initial count of turtles was taken on a small island. The population P is given by function P of t is equal to 175 times e to the 0.045 t, where t is the number of years since 2018. The second time the turtles were counted, their population was 250 turtles. How many years had passed after the initial count? And so we're given 250 turtles, right? And so this 250 turtles goes along with our population of turtles, because we have population and then we have time, where time is our variable. So if we were to set this equation up, we're going to have 250 is equal to our 175 e to the 0.045 t. And all we're doing at this point is solving for our t. And so then we can divide by 175 on both sides. So then we get, I don't know, just like 250 over 175 is equal to e to the 0.045 t. And then we can take natural log of both sides. And so doing that, that cancels out the natural log and the e, and that brings this 0.045 t in front. So then we're left with 0.045t is equal to natural log of 250 divided by 175. And then we can divide by 0.045 on both sides, right? So then we get t is equal to natural log of 250 divided by 175, and then that whole thing over 0.045, or if we evaluate that, we'll get 7.93 years. All right, so for part B, it says, assuming the population of turtles continues to grow at the same rate, by what percentage should the population increase in a decade? So 10 years. And so just a reminder, we have our function p of t is equal to 175 e to the 0.045t. And it wants to know by what percentage should the population increase in a decade. And so we're going to have, well, our equation is essentially going to be set up as like p of 10 is equal to 175 times e to the 0.045 times 10, right? And we know that this e to the 0.045 times 10, that's like our growth factor, right? Like the factor that it's growing by compared to our initial amount. And so we can just calculate for this. And we can say, all right, e to the 0.045 times 10, that's equal to our growth factor of 1.5, let's see, I'll just say 5683. And so if we subtract 1 from that, so I'll say like we can get our percentage that it grows by. So we'll have 1.5683 minus 1, and then we're going to multiply that by 100% to get it as a percentage. And then we'll get that it grows by, looks like 56.83%. All right, so for number 30, it says, suppose it takes a radioactive substance 36 years to decrease by 25%. Assuming there were 50 milligrams initially, find a formula y is equal to a times b to the t. All right. So, yeah, the key word here, you can see it's underlined, decrease by 25%. So if it's decreasing by 25%, that means it must be 75% of its original value, right? And so if we set this up, we'll have, so we know our initial was 50 milligrams. So we know that we're going to have an equation 50 times b to the t for some y. And it says it takes 36 years to decrease by 25%. So like I said before, we're going to have, didn't mean to do that. We're going to have 0.75 times our initial amount, and then that's going to be equal to 50 times b to the 36, right? Because it took 36 years to do that. And so then we can divide by 50 on both sides, so then we get 0.75 is equal to b to the 36. All right, so then if we do that, we can kind of, take root 36 of both sides. So then if we do that, I'll put that in my calculator real quick, 36.75, we get b is equal to, and it says 3 decimals, 0.992. Okay, so then if we set that up as our equation, we'll get y is equal to 50 times 0.992 to the t. All right, so for part B, it says how long will it take the same radioactive substance to decrease to 25% of its original mass? So to 25% of its original mass is going to be 0.25 times our original mass, right? So we'll have this 0.25 times our original of 50, and that's going to be equal to 50 times, well, we know our growth factor now, that's 0.992 to the t, and we're solving for our t, right? So then we can divide by 50 on both sides, and then we'll be left with 0.25 is equal to 0.992 to the t. And then we can use our handy log rules, since if we take the log of both sides, we know that if we have something in the log that's being taken to an exponent, we can just bring it out in front. And so then we'll have log of 0.25 is equal to t log of 0.992. And so then we can just divide by log of 0.992 on both sides. And so then we'll get t is equal to log of 0.25 over log of 0.992, or I'll just say t is equal to, if we evaluate that, we'll get like 172.6 years, and that should be a 0.6, 172.6 years. Alright, so for 31, it says a tennis ball is shot vertically upward from a height of 6 feet above the ground. At time 3 seconds, it was at its highest point of 177 feet above ground level. And now it wants to find a quadratic formula for the height in feet above the ground at time t seconds after it was shot upward. Okay, so if we think about this, just like in practical terms, and we know there's going to be a quadratic function, we know that we're going to have it start, I don't know, let's say here, and it's going to kind of go up and then come back down, right? And it says it hits its highest point right there. And so, and it tells us the highest point at time 3 seconds, and its highest point is at 177. And with this looks like a vertex, right? So what we can do is we can put this in vertex form. I think that would be the easiest way to solve this. And so we know we're going to have this, I don't know, this height function is going to be equal to some constant a, because there could be a multiplier there, and we know it's going to be t. So if our vertex is, 177, we know that then we can put it in the vertex form t minus 3, and then that's going to be squared plus 177, right? And now we don't know this a, but we can find it because it says a tennis ball is shot vertically upward from a height of 6 feet above the ground. So at the time that it was shot, at 0 seconds, it was 6 feet above the ground, right? So we can use this point to solve for our a. And so then we're going to have 6 is equal to a times 0 minus 3 squared minus plus 177. And so then if we subtract 177 on both sides, we'll get negative 171 is equal to a times negative 3 squared. So negative 3 squared is just going to be 9, right? So then we can divide by 9 on both sides. And so if we divide by 9 on both sides, we'll get a is equal to negative 171 over 9, or negative 19. And so then we can put that in. Now that we have our a, we can say our height function, h of t, is equal to negative 19 times t minus 3 squared plus 177. So on part B, it asks for the height of the ball at 5 seconds. So what we're going to be doing is just taking our equation that we came up with and finding it when t equals 5. And so we're just going to be finding h of 5 here. And so that's going to be negative 19 times 5 minus 3 squared plus 177. So then if we put that in our calculator, we'll get h of 5 is equal to, let's see here, 101 feet. All right, so we have on number 32, it says find a formula for a quadratic function with zeros at x equals -2 and x equals 5 that passes through the point -1, 8. So since we're given zeros, we know that our equation is going to be in the form of, like, let's say if we have zeros at x equals b and x equals c, we know that our equation is going to be in the form of y equals a times x minus b times x minus c, right? So that's kind of going to be the setup of our equation. So I'm just going to erase all of this and use the values that were given. And so we know that y is going to be equal to a times x minus a -2 times x minus 5, right? And so we don't know our a, but we are given a point. And so we can use that point to solve for our a, just like, kind of like we did in number 31. And so let's do that. So we're going to have 8 is going to be equal to a times our -1 plus 2 times -1 minus 5. And so then we get 8 is equal to a times 1, right, times a -6. And so then we get a is equal to -8 over 6 or -4 over 3, right? So then we can just plug that into our equation and we'll get an equation of y is equal to -4 over 3 times x plus 2 times x minus 5. That's number 32.